Okay, off we go. So, welcome back. I hope everybody had a good break. Don't forget about the attendance quiz, attendance code. Clock's ticking on that. You've got a little over a minute left, so make sure to get that code in. You may be out of the habit because of break, so there's your reminder. Okay, so we were talking about triple integrals, and I'm going to do a little bit of a rewind and, hit some major highlights. We don't have time to go through everything again, of course, but I do want to hit some highlights. The big idea of a triple integral is that it's a lot like a double integral. We're going to kind of rip off the idea of a double integral, which itself is a rip off of single variable integrals. All integrals have the feature that in some sense or another you're going to chop up into pieces and then add up the pieces. What I like to call the chop it up, add it up strategy for problem solving, right? So it's just that now we're talking about a three-dimensional solid, and when you chop up a three-dimensional solid, you get little pieces that look like this, little sub-boxes. And if the quantity in question is susceptible to a chop it up, add it up argument, in other words, if the whole is the sum of the parts, very important that this be the case, right? Not every quantity of interest has this feature, what I like to call an accumulating quantity. But if your quantity, like let's say mass has the feature that the whole is the sum of the parts, right? Then you can write the whole then as literally a sum of individual parts. And then on any individual piece, the idea is, in many cases at least, and this is what we need to be able to make an argument work, I need the quantity in question for your little piece to be some function times size. And here, of course, triple integral, we're talking about little pieces of volume, so these are volumes. So the quantity has to be something times size. Now, I'd like to, let me say that in a different sort of grammatically, active, passive, I don't know, say it a little bit differently. If the quantity is something times volume, that something is quantity per unit volume. So I like to think of the integrand as being a density. It's morally a density. And it's a really, really convenient point of view, kind of a nice broad stroke. You can always think of your integrands as being densities. So this, and of course we know sometimes it's literally density, right? If we're interested in mass, what do I multiply by volume to get mass? Well, mass per unit volume, literally density. Okay. All right, so that's what a triple integral is. Terminology, notation. Be careful with how you visualize these things. I'm not going to go through this argument again, but this is a little bit dangerous. Keep in mind that this is a losing deal right here, right? So that makes this correspondingly a little bit of a bad point of view because it sets you up to think about triple integrals in a way that you can't. So I'm not saying you shouldn't do that at all. I'm not saying it's a bad point of view, but it's I'll say that. There's some good things about it, some bad things about it, right? And what I want to encourage and what I think is ultimately the better point of view anyway, try not to think about just everything in terms of graphs. That's a single variable calculus point of view, right? Graphs are great in single variable calculus. But I think in general, it's better to think about integrals as, again, accumulations. Chop it up, add it up. Here we got stuff distributed over an interval that we're adding up. Here we've got stuff distributed over a two-dimensional region. We're adding it up. Here we've got stuff distributed over a volume. Same idea. Right? Nothing creepy, nothing crazy. No four-dimensional references, right? This is just a better way to think about what's going on. Okay. And by the way, when we get to chapters 6 and 7, and I know I say that a lot, but that's because chapters 6 and 7 are very, very idea heavy. This point of view, this is what I'll call density point of view on integrals is going to be very, very valuable. The graph point of view, it's just not going to be very helpful. So make sure to at least be able to think about things from this point of view. Okay. Okay, so, and let's see here. We were halfway through page 113, I think, and here we are on page 113. Okay, so, yeah, I think we talked about this diagram. So, I can't make this justification for you. The reason I can't make that justification is because for double integrals, this was volume. We computed volume two different ways and therefore concluded that the two different results we got must be the same. Well, now, this is a four-dimensional thing that I can't, there's no geometric appeal that I can make there, and so the argument kind of goes away. But it remains that this is true. It does remain, and that's what this theorem here says, that triple integrals can be computed with iterated integrals. And, you know, how do we know this is true? Well, there is a perfectly not only valid, there's a better argument, more rigorous argument that's purely algebraic. You don't need any geometric intuition that shows that this is true. And the reason I don't show you that argument is that it's what I'm going to call detail heavy. There's some subtleties and non-obvious statements about moving summations in and outside of limits. There's some real delicacies and bad things can happen. And I find it... well, anyway, I'll say there's not a lot of geometric satisfaction down that road. So I'm just going to assert that this is true, and I think it's pretty believable. Okay. All right. So that sort of completes our strategy for computation. Whatever your application is, write it as a triple integral, cite the fact that triple integrals can be computed with iterated integrals, and then we plug and chug on the iterated integral with the fundamental theorem of calculus. So let's do one. Y'all will probably recognize this first example. Not that we've seen it before, but we've seen something morally equivalent. Right, our first example with double integrals. We had mass distributed over a two-dimensional rectangle. Here we have mass distributed over a three-dimensional rectangular box. Step one. Quantity is computed with a triple integral. Step two. Triple integrals can be computed with iterated integrals. Step three is the what I'm going to call the plug and chug. We'll go through a couple of those details in a second. But there's your big picture, step 1, 2, and 3. Do notice that the punchline to that is all you got to do is you do have to give me the triple integral. I'm going to call that a small ask, right? Look how little it was to write down. The reason I think this is important is that one thing that I have highlighted in red here. That's what distinguishes your work from if someone were instead to just claim that you can compute things like mass with iterated integrals directly, which again, fraught, at best, fraught. There's awkward little details that have to be established to make that an actually analytically reasonable argument, and it's completely unnecessary, right? So this is a bad argument here, and all you got to do to distinguish your work from a bad argument is this one little thing. Just give me that. Does that make sense to everybody? And this is points, right? I mean, again, glass half full, glass half empty. Think of this as easy money. Free points almost. Right? You just got to recognize what is that triple integral that this represents. Okay. All right. The rest of this is pretty analogous. What's the range of values for y? Well, it's the range of values for y that was given. Right? What are the bounds for x? Well, it's the range of values of x that was given, etc. Right? What's the range of values for z? Well, again, it was given. Happy? Everybody good with that? Okay. Again, be careful to keep track of what's constant and what's not constant. Let's see here. Let's look at this integral here, the insidemost integral. In that integral, notice x and y are further to the outside. That means x and y are constants. And so all of this is constant, right? And so when it comes to actually doing this integral, z is our variable. The z antiderivative of 2z is z squared. Is that cool? Is everybody happy with that? Very important to keep track and make this part of your job, right? Is to make sure to keep track of which variables are playing what role at what stage of the calculation. Does that sound familiar, by the way? It's the exact same thing we talked about with double integrals. It's just, a little bit more so. But same basic idea as with double integrals. And I think it's fair to say the rest of this is plug and chug details. And I'm going to encourage y'all to go through the rest of these details. Make sure you're good with all of this, and we'll go on and talk about more challenging things down in the next page. Okay, so let's talk about non-rectangular domains. I'm going to scroll back a ways. Whoops, right, I went too far. There we go. When we had two-dimensional non-rectangular domains, remember the big idea was that, you're still chopping it up into little slices, right? And then we noticed that really the only difference is that these lower bound here, that lower bound is going to come from now a curve instead of a line, and so the lower bound is a function, in this case a function of y. And then likewise the upper bound, what's that upper bound going to be? Well, it's going to come from this curve, and it's going to be a function of y, right? Otherwise, everything is pretty much the same, right? We also made the realization that you don't have to draw the graph picture. The thing that determines these bounds, it's just a matter of looking at the domain itself, right? So we streamlined the process by saying, fooey on this picture, we're just going to draw this picture. It's still the same domain, and I just have to identify what are the relevant curves, right? We solve for the relevant bounds. Let's look at the upper bound. The upper bound is going to come from points that look like that are on certain curves that have certain equations in which I can solve for what I need. And it's going to be the same process. Now, can't justify that with a three-dimensional version of the argument because, again, the argument kind of relied on starting with this graph picture. That would be four-dimensional in our triple integral case. So I'm not going to justify it, but I'm going to claim that, look, the big idea is just keep track of how you move over the domain. And we're basically going to be slicing up the domain and keeping track of the ranges of values of various variables as we move over the whole domain. Same takeaway. We're just not going to make that argument. Is that cool? Is everybody on board? So let's walk through what that actually looks like. There we go. And it is a harder picture. And by the way, this is the way it is. So there's going to be a lot of pictures that we're going to be drawing to solve problems like this. You're going to have to be able to visualize things geometrically. This is not a method. This is the material. This is what the course is, right? This unavoidably, this material is geometric. It's literally about geometry. And so you're going to have to be able to visualize things geometrically, and you're going to have to, as an assistant to yourself, draw geometrically, right? So that you have something to work off of. And then, by the way, keep in mind as well, you got to communicate your ideas, and a good picture is a very important tool for communicating geometric ideas. Right? So to make sure you take the time to become at least decent at drawing pictures, I'm not going to grade the quality of your drawings. Right? That's not what we're here for. But unavoidably, I am going to I'm going to have to make interpretations of what ideas did you communicate, and if your ideas don't get communicated, because the drawing is unclear, I don't know what I'm looking at here, then the point is it didn't communicate the ideas. Does that make sense to everybody? So it's just unavoidably important to be able to do decent drawings. Okay. Okay, so let's go through this process. Arbitrarily, I'm going to do my slicing with the differentials in this order. There's 6 different ways to arrange those differentials. They're all valid. Take your pick. We'll talk more in a minute about how to make good choices there. For the moment, let's just make this choice for this random picture I've got here. Okay, starting with x. For a given value of x, here's what an x slice looks like. It's not a line segment anymore. Now the x slice is an area. Now we got to think about first and last if we're interested in the bounds for x. So where is the first such slice? Where is the last such slice? And geometric appeal, the last such slice is whatever point here is kind of the farthest back into the page here. There's some point back there that's the farthest point back, and that will correspond to some value of x. Is that cool? Likewise, the last value of x, the last x slice will be some point, kind of whatever point is the nearest there, and that will have some value of x. And that gives me my x bounds. Okay. Now, as usual, just like with double integrals, we're now going to fix a value of x. We're going to choose an arbitrary value of x. We're going to look at, therefore, a particular x slice. And now we move on to the next variable. So, okay, on that x slice, what's the deal with y? Now, there's a geometry visualization thing. There's no way around it. If I'm going to look at a y slice, whoops, I wanted to be in pencil mode. If I'm going to look at a y slice here, I'm going to be taking a cross section there perpendicular to the y-axis, and you got to use your 3D visualizing. If I have this x slice and then I slice it perpendicular to the y-axis, I claim that I get a little line segment about like that. What do you think? Everybody see that? Okay, so again, the usual games, first and last. Where is the first of these? Where is the last of these? Well, the first one's going to be here. Whatever the leftmost point that is, keeping in mind on the x slice, right? We're only interested in that x slice. Other values of y, like you might make the argument. Check out these points over here. Let's say how about this? At this point over here. This point over here. Well, I think y might be lower there than it is here. Why are we looking at this point, not that point? Here's the thing. We will get to this point for a different x slice. So don't worry about that, right? We'll get the whole solid. What we are interested in is how the y bounds depend on x. And so we look at one x slice at a time, right? We look at the y bounds for each individual one x slice at a time, and it will be a function that will depend on x, and that will give us the whole solid. Does that make sense to everybody? All right. Okay, so that value of y is our lower bound, and it's going to depend on x. Again, geometric imagination. Imagine different x slices, as I move across this lumpy solid, different x slices will have different leftmost points, which will give you different y lower bounds. And that's how y1 is a function of x. All right, and then the largest value of y is going to come from that point, and that's going to correspond to a value of y. That's your upper bound. Is everybody happy? Yeah.
Why is it only dependent on x?
I'm sorry, say it again.
Why is it only dependent on x and not x and z?
Right, because we haven't gotten to z yet. We haven't even started thinking about z yet, right? So different x slices will give me different y bounds. But if you say, what about different z slices, I'm going to say, what are you talking about? I didn't even bring up z yet, right? I mean, by the way, notice these points here will have different z coordinates too. I just don't care because we're not thinking about z yet. Is that cool? Yeah. But we will get to z very next thing. Anybody else? Okay. So now again, we fix a value of y, and here's the thing, we already fixed a value of x. So in addition to having fixed a value of x, we're now also going to fix a value of y. And you might say, within both of these fixed, it's like we're picking a point in the xy plane. You might say a point sort of in the shadow, in the projection. And now for that fixed x and that fixed y, in other words, on this, you might think of that as a y slice of our x slice. Right? Now we move on to asking the next question, which is, let's think about what is the lower bound for z. The lower bound for z is going to come from that point, right? This lower bound for z, it's going to depend on where that sort of starting point for z is as I move along that green slice. So I'm going to have to figure out where that point is. It's going to depend on both x and y, right? You pick different x's and y's, that's going to give you different points down here. We'll be moving around in the sort of the xy plane differently. We're going to get different lower bound points for z. And then, likewise, the upper bound for z, well, that upper bound is going to come from that point. And again, we're going to have to do some algebra to solve. How are we doing? Is everybody happy? Okay, so do keep in mind, and now the following is analogous to stuff we've talked about for double integrals, but when you are looking at the inside integral, the inside most of the three integrals, keep in mind what that is, right? This is letting z range over certain values. That integral is happening, moving, you might say, across that sort of line segment. And on that line segment, keep in mind where that came from. That came from having already fixed values of x and y. And that means x and y, for the purposes of this inside integral, are constant. And we're going to treat them as constants because they are literally constants in the picture. Does that make sense? Okay. Okie dokie. Let's do one. Dive into this example. Now, there are different ways you could approach this, I suppose. I'm going to do this kind of head on, so that y'all can see what the process is. This is the general process that I think is the most reliably. I mean, this is what an iterated integral is. Just for your consideration, there is a streamlining of this process, a very valuable and convenient streamlining, and I will get to that next. But I want to make sure we see the underlying process first, and then I'll show you the slicker way to do it. Which, by the way, works sometimes, but not always, and so it's important to know the underlying method. Okay, so we have here tetrahedron, like so. And let's see here. We want to rewrite a triple integral as an iterated integral. We've got to figure out what these bounds are. Where did the triple integral come from? Whatever, who cares? Let's suppose that there's some quantity we're interested in. That's the triple integral that represents it. Okay. Which way are we going to do our differentials? We got 6 options. In this case, they're all kind of equally convenient. So it kind of doesn't matter in this case. I'm going to do it this way just to get the ball rolling. The remaining examples we'll do for the rest of class, I'll do in different orders. All right, but again, just to get the ball rolling, we'll do it like this, and that means that we start with our x slicing. So what do x slices look like? Well, there's the x-axis. This is what it looks like when you take a constant value of x. That is an x slice. And our x slice of our solid, in this case, is a triangle like that. Quick pause. How are we doing? Does everybody see that part of the picture? Okay, first and last. Where is the first such slice? Well, it's there. There's my first such slice. I'm interested in x. That first slice represents the lower bound for x. I think it's pretty clear that's where x is 0. After all, that first x slice is literally in the plane x equals 0. Is that cool? Everybody happy with that? Sometimes you get freebies. Sometimes they're easy. Okay. Generic slice. The further you go over, the more it looks sort of smaller and smaller, and the last slice will be at that point. Here we're going to have to do a little bit of work. Here it's not going to be immediately, I can't just sort of look at the picture and instantly say, oh, that's obvious. So what can I say about that point? Here's the thing. I know various things about that point, and the reason I know various things about that point is because I got a picture. I can see it from the picture. The picture is going to be unavoidably essential here. So here we go. The picture tells me that that point is in that face. Right there in the picture. That face has that equation, which I'll write down there. Now, what else do I know about that point? Well, again, from the picture, I can see that that point is on this face. The picture is what tells me that. That face has that equation. Let's write that down there. Lastly, again, you got to credit the picture for this. That green point that we're interested in is in this face, which has that equation. So, looking at x, trying to find the upper bound for x, looking at that point, I know that that value of x has to satisfy these equations. Let's pause here real quick. Is everybody with me? Everybody see how I use the picture to identify what are the relevant equations? And notice, by the way, it's not on this face back here. We're not writing down that equation. It's not on that face. Right? Is everybody happy? Okay, so let's see. We are looking for an x value, so we will solve for x in that equation. And that gives me my upper bound for the x integral. What do you think? Let's see how that works. And again, I want to distinguish between, the question is not whether you understand how the bounds are 0 to 1. Right? Because there may be different ways that you might sort of think that's obvious from the picture or whatever. You maybe have some different intuition. The point here is I want to use this relatively easy example as a as an opportunity to outline what the general method is that will tell you these bounds. So it's not the values, it's the process by which we got to these values. Is everybody comfortable with that process? Okie dokie. Off we go. Fixing a value of x. Now we want to ask what's the range of values for y on our x slice. We know that our y slices of our x slice are going to look kind of like this. Right? Now again, be careful. I don't care about what's going on over there. We will get to this point. We will get to that point when, for example, x is 0. We'll get there. And we're not forgetting about this point. We need to know, though, how the y bounds, what you might call the second integrals, y bounds, how they depend on x. And so that's why we're interested only in the x slice. So don't step on that landmine. That's an easy sort of a fundamental mistake that will give you some dramatically wrong answers. So we're only looking at that x slice. And again, we play the game first and last. The first slice is there, where y is obviously 0. I mean, it's literally in the xz plane where y is 0. So, of course, my lower bound is 0. Take the easy ones when you can get them. The upper bound, as I slice more and more, that last value of y there, whoops. Again, we're going to have to do a little bit of work. This upper bound, well, okay, let's play the usual game. It is pretty clearly in this face here, which has that equation. So let's write that down. It is also, picture tells me, pretty clearly on that face. Equation given. We'll write that thing down. And here's what's easy to forget. Very easy to sort of lose track of what's going on. Keep in mind, all of this is happening on our given x slice for our now arbitrarily fixed value of x. Right? So x is known. Right? And while we're thinking about our y bounds, we want our y bounds in terms of x, and so I treat x as a known. X is what it is. And I don't know why I just find writing this, x equals x, it looks kind of goofy. And it probably is, and that's okay. But this is, to me, this is a satisfying reminder to myself that I know what x is, and my answer is allowed to depend on x. Is that cool? Is everybody on board with that? Okay, so again, what am I doing here? It's easy to lose track. I am trying to find what is, let's leave that question mark there, what is the upper bound for y? So in this algebra, I need to solve now for y. And that gives me 1 minus x. Everybody happy? Okay. Proceeding along. Now we're going to take both y and x, arbitrarily fixed. Said differently, we're looking at, let's say, this y slice of our x slice. And now we play again, kind of the same game. I want to know what is the lower bound for z. Well, what's the lowest value of z anywhere on that green y slice of my x slice? It's going to come from that point. Sort of obviously in the plane z equals 0. So pretty easy to see that lower bound is 0. Again, you get freebies sometimes. That's great. And now, what do we get for the upper bound here? That's the upper bound for z. Well, that's going to come from that point. Is that cool? That point is on this face that has that equation. Don't forget x and y are known. Always check back. I feel the need to always check back. I'm trying to solve for z here because it's a z bound that I'm interested in. So in this algebra, I need to solve for z. That gives me this. And that makes my upper bound for z, like so. Everybody happy? Everybody see the process is the point. Okay, so that's the process. That's pretty much how they work. Couple of observations. Try not to slice through corners. Right? You've got 6 different ways that you can slice. If you find yourself slicing through corners, you know that means it's going to turn one integral. You're going to have to stop the iterated integral you're working on and start a new iterated integral. It's trouble, right? I mean, that's nobody wants to do that. So choose a different order to slice if you can, right? Almost always, if you can avoid slicing through corners, you should avoid slicing through the corner. Okay, and then likewise, keep in mind, whatever variables are on the inside, you're going to have to solve in the given algebra for that variable. So, yeah, put on the inside a variable that's going to be relatively easy to solve for. Right? Make your life simple. Don't make your life unnecessarily difficult. Okay. All right. So now what I have here is a summary of a streamlining of this process. I think is really valuable. I find this just really convenient. And I wish more books would spend time talking about this. I feel like that's not a common enough point of view. I think it's going to make more sense, though, to understand this summary after we've actually done one. So what I'm going to do is I'm just going to, for the moment, I'm going to skip this. We're going to dive into an example. And as the ideas develop, we'll go back and see how that's what the summary said. Okay. So, okay, let's see here. Oh, I got to get a lot onto the screen here. Okay, so difficult draw. You got a couple of surfaces. The surfaces themselves aren't that hard to draw, but this first octant portion of what's bounded by those surfaces is a little bit hard to draw. So this is, I would call this an art challenge. This is non-trivial. Side note, now I've pitched to y'all several times, I'm sure I'll do several more, that, you know, everything I know about mathematical drawing, I've got in these videos in my miscellaneous topics playlist. And I hope that'll help as you try to get better at drawing. Again, being able to make, this is not perfect, right? I'm not bragging about this drawing, but it's good enough. It's plenty good enough for our purposes, and it is important to be able to do plenty good enough. Anyway, the reason I mention this is in those recordings that I have, the first recording is various tips and tricks and things to keep in mind and things you should practice. The second recording is about specific examples of hard things to draw and how to draw them. And this is one of them. Right? So if you want to know how I drew this, and it took me a while, by the way, to make a decent drawing like this, but if you want to know what were the considerations and how did I know to angle this like that, why does this curve go upward there as opposed you'd think it would go horizontally, and how does this kind of all work and then kind of look halfway decent, I explain all of that in gory detail in that second recording. So I hope you'll find that useful. And again, you're going to need to be able to make respectable, decent drawing kind of like this. Okay, so first observation. I don't even have to see the picture. I see that algebra right there. I'm already scared of, I don't want to solve for x. I don't want to solve for y. I don't mind at all solving for z. No square roots, it's already done for me. That solving for z sounds good, right? So with that in mind, I'd rather solve for z whoops, missed, put the dz on the inside. Does that make sense? All right. And then process of elimination, that means x and y are going to be on the outside, like so. Okay, so now let's start doing our slicing. No particular reason we're doing dy on the outside. You could switch the x and the y or whatever, doesn't matter. So let's do dy on the outside. There's the y-axis. And let's see our y slices of our solid. There's the first one. And then here's kind of a generic y slice. And then here's the last one. Right? Okay. Here's another observation I'll make before we move along. What if I were to look at the shadow down here? Forget about the solid. Let's just look at the shadow. First slice. Generic slice. Last slice. And check it out. They're right on top of each other. Right? That as I slice up the solid, I am at the same time slicing up the shadow. So the observation here, when you're thinking about your y slices, you don't have to slice up the solid. By the way, thank God, right? I mean, look at this. This picture is hard to draw. The slices, it gets confusing and artistically challenging. Don't have to. Just look at the shadow. It's a lot easier to draw the shadow. It's easy to slice up and see what those slices look like. It's just an area in the XY plane. So much easier. Is that everybody with me? All right. Now let's move it along to doing the X slicing. As we go in the X direction, here's how I slice up in the X direction on the solid, the slice of our solid, and correspondingly, there's how I slice up the Y slice of the shadow. And again, they're right on top of each other, right? The first value of the first value of X for the solid is the same as the first value of X for the shadow. And the last value of X for the solid is the same as the last value of X for the shadow as well. So here's the big takeaway. This is a powerful takeaway. Once you've decided what differentials you have on the outside. Now again, I had my motivations, right, for sort of algebraic reasons. I'd rather put dx dy on the outside. Look at the shadow in the corresponding coordinate plane. Here, the xy plane. You can just look at that shadow. Don't slice up the solid. Slice up the shadow. And slicing up that shadow will give you all the correct bounds. Yeah? Is everybody happy with that? It's a pretty neat takeaway. Much easier to draw, much easier to slice. It's just an area. Y'all have been slicing up areas with double integrals for a while now, so no problem. Okay. All right, now having done that, it does remain, we've got the outer two integrals done. We do have to figure out what's going on with the inside integral. Let's see here, how am I going to do this? How do I find the range of values for z? Let me just do it like this. Keep in mind that this is just a mess. When I get around to doing the z bounds, x and y are fixed. That means we're looking above a single point there in the shadow. That single point in the shadow looks like this. And I just need to know where does z start, right? So I need to look at, this sort of starting value and ask, well, what's the corresponding z there? And then I just need to know where does it end? Well, it ends when I get there, and I need to know what is the corresponding value of z there. Z1 and Z2, those are my inner bounds. And sometimes, and this is a good case, sometimes that point that defines the lower bound is always on the same surface. Check it out. For this particular surface, no matter where you are in this shadow, the lower point of our slice is always on that green surface, consistently. No matter where you are in the shadow, the lower bound's always on that green surface. Does everybody see that? Okay. And then likewise, no matter where you are in the shadow, the upper bound is always on that surface. So we're always going from a consistently the same lower surface to a consistently the same upper surface. That's really convenient, right? And you can solve for z in those two equations. Let's see here. For the lower one, we need to solve for z there. We set it up so that'd be easy to solve for z. And then for the upper one, we solve for z there. And that one was easy too. So you do have to actually look at your solid at some point, right? To go those inner bounds, you do have to see the solid, but this makes it easier to kind of do the analysis very often. So this is what I'm going to call, these are the criteria, as I like to think of them, for when this is a good opportunity to use this projection argument. Keep in mind, for your outside two integrals, you're going to be slicing up the shadow. Make sure that shadow is something you'd like to slice up. Sometimes shadows are weird looking. If the shadow is weird looking, this might not be a good plan, right? Maybe you just kind of use the usual methods. We also capitalized pretty nicely on how that bottom surface was consistently the same surface, and that top surface was consistently the same surface. So that's a good thing to look for as well. Just you can look at the solid itself and think about what is my lower surface, what is my upper surface, and are they always the same? And if they are, then something along these lines is probably going to go pretty conveniently. And using this projection argument is pretty nice. How we doing? Does everybody kind of see the strategy there? Let me show you another example of this in action. The unit ball. This seems like it would be an easy one because it's such a routine shape, right? It's a ball. It's something kids play with. I mean, it is not scary, right? But look what the answer ends up being. It's got all sorts of square roots and stuff. This ends up actually being kind of hard to do and surprisingly difficult to draw. Doesn't seem like it would be, but if you take your unit ball and then think about what one of your X slices looks like. So there's the X direction. An X slice would be something like this. It already kind of looks suspicious because why is this slice sort of right on the edge? That doesn't quite seem right. I mean, over here, back here, it wouldn't touch the green horizon line. It can get a little confusing to draw. Right? Try it. It's harder than you would think it is. And then when you look at that cross section and you have to think about, okay, well, for example, I want to know for that value of X, for that X value, we look now at this X slice and I want to know what's the range of values of Z. Well, let's see here. Z is going to start there and end there. I'm going up here. My slices look like this. And then for any given one of those, Y goes like that. And it has, you can see that it gets a little confusing to draw. The picture gets weirder than you would think. And by the way, this is about the best I know how to do. Again, I probably took about 20 minutes to draw this figure. That's more trouble than you'd like to have to go to most of the time. Okay. All right. So let's take the projection point of view. We've got X and Z on the outside. Let's think about the shadow in the XY direction. The shadow is a disk And a disk in the XY plane is easy to slice up. So just, draw yourself the unit disk in the XZ plane. It's pretty easy to see that that's what that projection is in the XZ plane. Slice it up with double integral methods. This is what you'll get. You get to work off of a two-dimensional picture to do that. And then you notice, for any given value of X and Z, notice that your lower bound for Y will always be some point that's on that left surface. X squared plus Y squared plus Z squared is 1. And Y is negative. The upper bound for Y will always be a point over here on this right surface. Again, X squared plus Y squared plus Z squared is 1. This time with Y positive. In both cases, you solve for Y, boom, and we're done. And I think geometrically, that's easier in terms of, again, artistically and geometrically in terms of visualizing, I think that's easier than the slicing alternative. So, nice method. Okay, we're out of time. I'm sorry to go over. We'll pick up here next time. See y'all later. Welcome back.